In section 4, chapter 14, we have the assumptions of the multiple regression model. First assumption, we need to assume that there is a linear or straight line relationship between the dependent variable and the set of independent variables. You can do that by just getting a scatter plot for each independent variable, temperature versus cost, insolation versus cost. And if you right click on any of the dots and then you add a trend line, you should get a downward sloping line in this case. So that verifies that there is a straight line. The other assumption is that the variation in the residuals, y minus y hat, is unrelated to whether y hat is large or small. Remember, y hat is the estimated values of y. Going back to the last part of the section 3, the model was reduced to using cost as a dependent variable and temperatures and insolation as independent variables because age was not, the age of the furnace was not statistically significant. So we can estimate estimated cost, or y hat, is equal to my coefficient. In the model that I obtain, I have an intercept which I'm going to fix, and then plus my next coefficient for the temperature, which I fixed too. You can press F4 in Excel, times the corresponding temperature here in B2, and then plus the final coefficient fixed the cell times insolation. And that'll be a predicted value of y. And if I copy this to the rest, then I get all my predicted values. And the residuals are just the difference between the actual y, which is A2, minus F2, which is the estimated values of y. If I copy this, then I get all the errors. Now notice I have estimated cost next to the errors, so I can just select the two and insert a scatter diagram, and that verifies that all the errors, if you notice, are around the estimated values of y in an almost uniform way. So they are all scattered. It doesn't matter what the value of y hat is, you find all kinds of different errors, small and large, around the values of y hat. Now the values of y hat, you can also obtain them, and the residuals next to them. You can obtain them in Excel by just going to data again, data analysis, select regression. Let me see if this is the right range. But now I'm going to add residuals. And anticipating something else, I'm going to add what is called normal probability plots. And I'll explain later what that means. I'm going to override what I have. And if you notice, I get my predicted cost, 265.88. That's exactly what I get here, 282, 282.06. And the difference between y and y hat are the errors or residuals. They're shown exactly the same values, minus 1588, 7793, etc. Okay, so you can get that without making all this calculations. And the residuals are normally distributed with a mean approximately equal to 0. You can verify that the errors are normally distributed if you get, remember that I added a normal probability plot. If you right click here and you add a trend line on any of the dots, you can right click. And if the errors that are plotted here, if they are around, if they are pretty close to that line, as you see they are on that line, then normal probability occurs, or they are normally distributed. Something else you can do is you can get a histogram, as it's shown on this left-hand side graph, which is just taking the largest value of the errors minus the smallest values of the error, divided by 5, and you calculate the frequency of each class, and this should have been done in 3402, and you get approximately a normal distribution. And the residuals are normally distributed with the mean approximately equal to 0. That was the last thing we did. Number 4, the independent variables should not be correlated. That is, we use a set of independent variables that are not themselves correlated. So what is that? Well, when they are correlated, that is called multicollinearity. And multicollinearity causes problem in the model. You have changes in sign on independent variables, so you have significant changes in the coefficients. So you need to check for that possible problem. And one way you can do it is by getting a correlation matrix and check whether there is a correlation of 0.70 or higher in absolute terms between any two independent variables. The other test you can do is what is called the VIF that is shown here. Let me show you what each one of these is. In our set, multicollinearity may exist if we get, let me get the correlation matrix. First, you look for the correlation or calculate a correlation matrix. So go to data analysis, and then select correlation. Of course, Excel is going to calculate it for you. You click OK, and you just select all the, if you want, you can select all of them. But in this case, I mean, it depends on what you need. Maybe for your assignment, you need to select more variables. For this one, you just need 3 variables because these are the ones involved in the model. Labels on the first row, and I want my output right here. And my matrix in this case is very simple. Cost in relation to cost, of course, is 100. Temperature in relation to temperature, you know, in relation to itself is always 100% correlation. But this first column shows you how the two independent variables, temperature and insulation, are related to cost. Minus 0.81 and minus 0.2571. But you are not interested in that. You're interested in how the independent variables are correlated. And the only one that that we are interested in right here is the relationship between insulation and temperature, and that is minus 0.10. And as you can see, the absolute value is not greater than 0.70, because if it were greater than 0.70, then we will have multicollinearity. Okay, and so multicollinearity doesn't exist. And the other way you can do it is, suppose you suspect insolation is the one that causes multicollinearity, or temperature. And what you can do is just run a regression between insolation and temperature, insolation and temperature, using insolation as a dependent variable and temperature as an independent variable. And let me do that here. It doesn't matter the order, by the way. You can reverse that later, since you are using only 2 variables. And then you look at the R-square. Let me go back to data analysis, and I'm going to run another regression. But this time my dependent variable is going to be one of the 2 independent variables, temperature. And my independent variable is insolation. You select whatever is necessary, whatever is indicated in the model. If you have more than 2, you can use the remaining 3, remaining 4, remaining 5. As long as you're using the suspected variable, independent variable that causes multicollinearity as dependent variable, then they use the other ones as independent. In this case, we only have 2. So we check again labels and our output. I want it right here. I don't know if I'm going to use some of the other space. Let me uncheck residuals and normal. All right, so I used a little space from what I used before. This is not relevant anyway, so let me just delete this. And what we are interested in is in the in my result here, I'm looking at the R-square, which is notice that it's very small, 0.010612. And I'm going to run the regression right here. I'm going to obtain the regression. What if I use instead a insolation as the independent variable and temperature as a dependent variable? We can reverse that. You're going to get something interesting here. And my Y range is insolation. And my X range is temperature. And again, the same thing, except that I want my output right here. And notice that my R square is 0.0106. My R square here is 0.0106. It's exactly the same. Okay, so if you use the test for 2 variables, you just need to use it for 1. Okay, and that gives you the same R square. And what is the VIF? What is called VIF of the test that involves using the R square. So is equal to 1 over 1 minus R squared. Then let me just put the R squared. And my value is 1.01, which is not even close to 10. So the test that we were looking at here, VIF, or the variance inflation factor, is you calculate, after you run the regression between the 2 independent variables, using 1 as a dependent, you look at the R squared and calculate 1 over 1 minus R squared. And in our case, as I already showed you, this is a table using temperature, insolation, and age of the furnace. The first test, in the first test, notice none of them is greater than 0.78. And in the case of the R square, the VIF, the R square obtained is 0.241 because they use 3 variables instead of 2. But I only use the 2 because those are the only 2 that are significant. And in this case, the VIF is 132, which again is much less than 10. So therefore, there's no multicollinearity. And in my case, there is no multicollinearity because I get 1.01. So either way, you obtain no multicollinearity. And I use it with 2 variables because I think you have in your homework also a case like that. And the last assumption is that the errors do not show a trend. In other words, we don't have what is called autocorrelation. Let me go back to 21 here. The last assumption is that the residuals are independent. That means that successive observations of the dependent variable are not correlated. This assumption is often violated when time is involved with the sample observations. We're not looking much in detail on that one. And let me go back. Our last assumption of multiple regression is that the residuals are independent. That means that successive observations of the dependent variable are not correlated. And this assumption is often violated when time is involved with the sample observations. We're not looking at time or what is called time series. When successive residuals are correlated, we refer to this condition as autocorrelation. And you just get a scatter plot with the errors of the residuals. And if they show a trend like this one on top, then there is autocorrelation. And if they are scattered all around the values of y hat, as it is our case, then there is no autocorrelation. And that is the end of this section.